part of the jet, the liner does not have time to be fully accelerated before it forms its part of the jet. This results in its small part of jet being projected at a lower velocity than jet formed later behind it. As a result, the initial parts of the jet coalesce to form a pronounced wider tip portion. Most of the jet travels at hypersonic speed. The tip moves at 7 to 14 km forward/s. The jet tail at a lower velocity, 1 to 3 km forward/s, and the slug at a still lower velocity, less than 1 km forward/s. The exact velocities depend on the charge's configuration and confinement, explosive type, materials used, and the explosive initiation mode. At typical velocities, the penetration process generates such enormous pressures that it may be considered hydrodynamic. To a good approximation, the jet and armor may be treated as inviscid, compressible fluids, see, for example, 40, with their material strengths ignored. A recent technique using magnetic diffusion analysis showed that the temperature of the outer 50% by volume of a copper jet tip while in flight was between 1100 K and 1200 K, 41, much closer to the melting point of copper, 1358 K, than previously assumed. 42. This temperature is consistent with a hydrodynamic calculation that simulated the entire experiment. 43. In comparison, two-color radiometry measurements from the late 1970s indicate lower temperatures for various shaped charge liner material, cone construction and type of explosive filler. 44. A Comp B loaded shaped charge with a copper liner and pointed cone apex at a jet tip temperature ranging from 668 K to 863 K over a 5-shot sampling. Octal-loaded charges with a rounded cone apex generally had higher surface temperatures with an average of 810 K, and the temperature of a tin lead liner with Comp B fill averaged 842 K. While the tin lead jet was determined to be liquid, the copper jets are well below the melting point of copper. However, these temperatures are not completely consistent with evidence that soft recovered copper jet particles show signs of melting at the core while the outer portion remains solid and cannot be equated with bulk temperature. 45. The location of the charge relative to its target is critical for optimum penetration for two reasons. If the charge is detonated too close, there is not enough time for the jet to fully develop. But the jet disintegrates and disperses after a relatively short distance, usually well under 2 meters. At such standoffs, it breaks into particles which tend to tumble and drift off the axis of penetration, so that the successive particles tend to widen rather than deepen the hole. At very long standoffs, velocity is lost to air drag, further degrading penetration. The key to the effectiveness of the hollow charge is its diameter. As the penetration continues through the target, the width of the hole decreases, leading to a characteristic fist-to-finger action, where the size of the eventual finger is based on the size of the original fist. In general, shaped charges can penetrate a steel plate as thick as 150% to 700%, 46, of their diameter, depending on the charge quality. The figure is for basic steel plate, not for the composite armor, reactive armor, or other types of modern armor. Liner. The most common shape of the liner is conical, with an internal apex angle of 40 to 90 degrees. Different apex angles yield different distributions of jet mass and velocity. Small apex angles can result in jet bifurcation, or even in the failure of the jet to form at all. This is attributed to the collapse velocity being above a certain threshold, normally slightly higher than the liner material's bulk sound speed. Other wideliest shapes include hemispheres, tulips, trumpets, ellipses, and biconics. The various shapes yield jets with different velocity and mass distributions. Liners have been made from many materials, including various metals, 47, and glass. The deepest penetrations are achieved with a dense, ductile metal, and a very common choice has been copper. For some modern anti-armor weapons, molybdenum and pseudo-alloys of tungsten filler and copper binder, 9-1. Thus density is almost equal to 18 mg/m3, have been adopted. Nearly every common metallic element has been tried, including aluminum, tungsten, tantalum, depleted uranium, lead, tin, cadmium, cobalt, magnesium, titanium, zinc, zirconium, molybdenum, beryllium, nickel, silver, and even gold and platinum. The selection of the material depends on the target to be penetrated. For example, aluminum has been found advantageous for concrete targets. In early anti-tank weapons, copper was used as a liner material. Later, in the 1970s, it was found tantalum is superior to copper, due to its much higher density and very high ductility at high strain rates. Other high-density metals and alloys tend to have drawbacks in terms of price, toxicity, radioactivity, or lack of ductility. 48. For the deepest penetrations, pure metals yield the best results, because they display the greatest ductility, which delays the breakup of the jet into particles as it stretches. In charges for oil well completion, however, it is essential that a solid slug or carrot not be formed, since it would plug the hole just penetrated and interfere with the influx of oil. In the petroleum industry, therefore, liners are generally fabricated by powder metallurgy, often of pseudo-alloys which, if unsintered, yield jets that are composed mainly of dispersed thin metal particles. Unsintered cold-pressed liners, however, are not waterproof and tend to be brittle, which makes them easy to damage during handling. Bimetallic liners, usually zinc-lined copper, can be used. During jet formation, the zinc layer vaporizes and a slug is not formed. The disadvantage is an increased cost and dependency of jet formation on the quality of bonding the two layers. Low melting point, below 500 degrees Celsius, solder or braze-like alloys, for example, SN50PB50, ZN97.6PB1.6, or pure metals like lead, zinc, or cadmium, can be used. These melt. Before reaching the well casing, and the molten metal does not obstruct the hole. Other alloys, binary eutectics, for example PB88.8 SB11.1, SN61.9 PD38.1, or X71.9 CU28.1, form a metal matrix composite material with ductile matrix with brittle dendrites. Such materials reduce slug formation but are difficult to shape. A metal matrix composite with discrete inclusions of low melting material is another option. The inclusions either melt before the jet reaches the well casing, weakening the material, or serve as crack nucleation sites and the slug breaks up on impact. The dispersion of the second phase can be achieved also with castable alloys, for example, copper, with a low melting point metal insoluble in copper, such as bismuth, 15% lithium, or up to 50%, usually 15-30%, lead. The size of inclusions can be adjusted by thermal treatment. Non-homogeneous distribution of the inclusions can also be achieved. Other additives can modify the alloy properties. Tin, for 8%, nickel, up to 30% and often together with tin, up to 8% aluminium, phosphorus, forming brittle phosphides, or 15% silicon form brittle inclusions serving as crack initiation sites. Up to 30% zinc can be added to lower the material cost and to form additional brittle phases. 49. Oxide glass liners produce jets of low density, therefore yielding less penetration depth. Double-layer liners with one layer of a less dense but pyrophoric metal, for example aluminum or magnesium, can be used to enhance incendiary effects following the armor-piercing action. Explosive welding can be used for making those, as and the metal-metal interface is homogeneous, does not contain significant amount of intermetallics, and does not have adverse effects to the formation of the jet. 50. The penetration depth is proportional to the maximum length of the jet, which is a product of the jet tip velocity and time to particulation. The jet tip velocity depends on bulk sound velocity in the liner material. The time to particulation is dependent on the ductility of the material. The maximum achievable jet velocity is roughly 2.34 times the sound velocity in the material. 51. The speed can reach 10 km/s, peaking some 40 microseconds after detonation. The cone tip is subjected to acceleration of about 25 million g. The jet tail reaches about 25 km/s. The pressure between the jet tip and the target can reach 1 terapascal. The immense pressure makes the metal flow like a liquid, though X-ray diffraction has shown the metal stay solid. One of the theories explaining this behavior proposes molten core and solid sheath of the jet. The best materials are face-centered cubic metals, as they are the most ductile. But even graphite and zero-ductility ceramic cones show significant penetration. 52. Explosive charge. For optimal penetration, a high explosive with a high detonation velocity and pressure is normally chosen. The most common explosive used in high-performance anti-armor warheads is HMX, Octagon, Althauf, never in its pure form, as it would be too sensitive. It is normally compounded with a few % of some type of plastic binder, such as in the polymer-bonded explosive, PBX, LX14, or with another less sensitive explosive, such as TNT, with which it forms octol. Other common high-performance explosives are RDX-based compositions, again either as PBXs or mixtures with TNT, to form composition B and the cyclotols, or wax, cyclonites. Some explosives incorporate powdered aluminum to increase their blast and detonation temperature, but this addition generally results in decreased performance of the shaped charge. There has been research into using the very high-performance but sensitive explosive CL-20 in shaped charge warheads, but, at present, due to its sensitivity, this has been in the form of the PBX composite LX19, CL-20 and Estane binder. Other features. A wave shaper is a body, typically a disc or cylindrical block, of an inert material, typically solid or foamed plastic, but sometimes metal, perhaps hollow, inserted within the explosive for the purpose of changing the path of the detonation wave. The effect is to modify the collapse of the cone and resulting jet formation. With the intent of increasing penetration performance. Wave shapers are often used to save space. A shorter charge with a wave shaper can achieve the same performance as a longer charge without a wave shaper. Another useful design feature is subcalibration, the use of a liner having a smaller diameter, caliber, than the explosive charge. In an ordinary charge, the explosive near the base of the cone is so thin that it is unable to accelerate the adjacent liner to sufficient velocity to form an effective jet. In a subcalibrated charge, this part of the device is effectively cut off, resulting in a shorter charge with the same performance. Variance. There are several forms of shaped charge. Linear shaped charges. Linear shaped charge. A linear shaped charge, LSC, has a lining with V-shaped profile and varying length. The lining is surrounded with explosive. The explosive then encased within a suitable material that serves to protect the explosive and to confine, tamp, it on detonation. At detonation, the focusing of the explosive high-pressure wave as it becomes incident to the sidewall causes the metal liner of the LSC to collapse, creating the cutting force. 53. The detonation projects into the lining, to form a continuous, knife-like, planar jet. The jet cuts any material in its path, to a depth depending on the size and materials used in the charge. Generally, the jet penetrates around 1 to 1.2 times, 54, the charge width. For the cutting of complex geometries, there are also flexible versions of the linear-shaped charge, these with a lead high-density foam sheathing and a ductile forward/flexible lining material, which also is often lead. LSCs are commonly used in the cutting of rolled steel joists, RSJ, and other structural targets, such as in the controlled demolition of buildings. LSCs are also used to separate the stages of multistage rockets. Explosively formed penetrator. Formation of an EFP warhead. USAF Research Laboratory. The explosively formed penetrator, EFP, also known as the self-forging fragment, SFF, explosively formed projectile, EFP, self-forging projectile, SFP, are the products of a shaped charge. An EFP uses the action of the explosive's detonation wave, and to a lesser extent the propulsive effect of its detonation products, to project and deform a plate, dish or cone of ductile metal, such as copper, iron, or tantalum, into a compact high-velocity projectile slug, rod or jet. This EFP is projected toward the target at about 2 km per second. The EFP is relatively unaffected by first-generation reactive armor and can travel up to perhaps 1,000 charge diameters, CDs, before its velocity becomes ineffective at penetrating armor due to aerodynamic drag, or successfully hitting the target becomes a problem. The impact of the EFP normally causes a large diameter but relatively shallow hole, of, at most, a couple of CDs. If the EFP perforates the armor, spalling and extensive behind armor effects, BAE, also called behind armor damage, BAD, will occur. The BAE is mainly caused by the high temperature and high velocity armor and fragments being injected into the interior space and the blast over pressure caused by this debris. More modern EFP warhead versions. Through the use of advanced initiation modes, can also produce long rods, stretched slugs, multi-slugs and finned rod forward/slug projectiles. The long rods are able to penetrate a much greater depth of armor, at some lost BAE. Multi-slugs are better at defeating light or area targets and the finned projectiles are much more accurate. The use of this warhead type is mainly restricted to lightly armored areas of main battle tanks, MBT, such as the top, belly and rear armored areas. It is well suited for the attack of other less heavily protected armored fighting vehicles, AFV, and in the breaching of material targets, buildings, bunkers, bridges or ports, etc. The newer rod projectiles may be effective against the more heavily armored areas of MBTs. Weapons using the EFP principle have already been used in combat. The smart submunitions in the CBU-97 cluster bomb used by the U.S. Air Force and Navy in the 2003 Iraq War employed this principle, and the U.S. Army is reportedly experimenting with precision-guided artillery shells under Project Saddam, Seek and Destroy Armor. There are also various other projectile, bonus, DM-642, and rocket submunitions, Motive 3M. DM-642, and mines, MIF, TMRP-6, that use EFP principle. Examples of EFP warheads are U.S. Patents 5038683, 55, and U.S. 660691. 56, tandem warhead. Some modern anti-tank rockets, RPG-27, RPG-29, and missiles. TOW-2B, IRIX, HOT, Milan, use a Tundra warhead shaped